In this practice, we prepare the most commonly used solutions in the genetic engineering laboratory, making the necessary calculations and making use of the knowledge of the different types of concentration and the methods to be followed for each solution. The elaboration of solutions is an important part of the daily tasks of a genetic engineering laboratory, and it is important to know that there are different types of solutions with specific requirements and concentrations. A stock solution may be either a primary standard solution made with a pure chemical solute that enables the exact calculation of the concentration, or a secondary standard solution, which concentration is obtained by titrating against a primary standard solution and is determined by a stoichiometric calculation. Also, there are working solutions obtained by the accurate dilution of a primary or secondary standard dilution, which concentration is determined by a dilution factor calculation. Working solutions are made up in small quantities for use in the short term. The amount of solute and solvent in a solution can be quantitatively expressed using numerous concentration units, and the most common are molality, normality, molality, percent composition, and percent million. Here are the formulas with which each are obtained.
Often, in the laboratory, the preparation of different solutions is needed. Each one has specific stages in its preparation depending on its function. Therefore, the knowing about the particular requirements is critical to get a proper solution. The following chart flow is proposed as a general methodology for any type of solutions.
Once the solution is prepared, we can verify that it was prepared correctly, first visually, if no dissolving solute is observed. In the case of culture media, it is usually verified by its clear color and consistency. Chemically, it can be verified by means of a titration to verify that its concentration is the correct one.
In practice too, different solutions that are subsequently used in the laboratory work to carry out the preparation of any type of solution. The following steps should be: 2. A portion of the solvent is added to the flask. 3. The amount of the solute is weighed out, or the volume is measured. 4. The solute measured is transferred to the flask. Does it need to be heated? Yes, to run the heating grill. No, the mixture is stirred until all of the solute is dissolved. Does it need pH adjustment? Yes. 1. Place the electrode in the solutions and read. 2. If it's necessary, add hydrochloric acid of sodium chloride up to desired pH. 3. Add and now the solvent up to desired volume. No. Add and now the solvent up to desired volume. After, place in the storage bottle. Label. Doesn't need to be sterilized? No. Store in drawers or refrigerator at 4 degrees Celsius. Yes. Place in the autoclave. Does it need antibiotic? No. Store in drawers or refrigerator at 4 degrees Celsius. Yes. Add antibiotic and store in drawers or refrigerator.
The laboratory provides a Laurier-Bertani culture medium which is readily employed, as it is prepared in a powder mixture. Thus, to prepare solid and liquid medium, the mass of powder per unit volume specified by the manufacturer must be consulted, and the expression to calculate this value is very simple. For the calculation of Laurier-Bertani powder and agar, we employed the following equation, where M stands for the mass weight, and V for the target volume, and P for the proportion stated by the manufacturer. The calculated values are: culture medium B is prepared with 100 micrograms per milliliter ampicillin from a stock solution 100 milligrams per milliliter. Therefore, the employed equation is the following. Stock medium requires additional ingredients. These additional ingredients were obtained from 1 molar stock solutions. Using equation 2, the volumes added to the mixture are the following. For the preparations of solutions, some additional equations were employed, for example, molarity and volume or mass percentage. The results of the volumes and masses calculated to prepare the following solutions are shown in a table.
Most of the solutions used in genetic engineering, at least those prepared in this practice, are constituted by solution dissolved in liquids, generally distillated water or molecular biology grades. There are several concentrations that can be used as molarity. An example is that it helps us to prepare dilute acids from some concentrated solution of some acid with the help of the data provided by the manufacturer, like density, molecular weight, etc. Since normally these substances are originally more concentrated, or also it can be used in psychological solutions such as 140 millimoles sodium, which is used as intravenous saline solution. You can also use normality. It's used to know mainly concentrations. Molality, on the contrary of molarity, is not so common and is used in very specific calculations, especially in colligative properties. Normality, you can use it with electrolyte concentrations and it can be expressed in milliequivalent per liter and are also used in acid-base and redox processes. On the other hand, when using parts per million, we will be working with very dilute solutions such as water analysis or biological preparations. The percentage solutions depend on the concentration of the solute and the solvent, are usually used in some products of the industry, such as beer to represent its content, or in the pharmaceutical industry. Finally, there are also solutions prepared from stacks. These help us to know how many we should take from a solution that is more concentrated for the preparation of other solutions, as in the case of a buffer. In this type of preparations, you cannot use molarity, since we are preparing a solution from another already prepared.
Preparation of solutions, it is important to take into consideration different situations that may affect the final product and in consequence the performance of the method where we're implementing the solution. The most common mistake happens during the calculation of the solute needed to prepare the solution, so it is advised to double check the units that are being used for the calculations. It is also important to check the concentration at which the solution is available at the lab. For example, the hydrochloric acid is commercially sold at a 37% concentration, and the amount needed to prepare a solution will be different than if the concentration was at 100%. For the calculations, the content of water is also important because it affects the overall molecular weight. So according to the number of molecules of water in the solute is the number of times that the molecular weight of water will be added to the molecular weight of the solute. Once the result is confirmed, if this one is in a solid state, it is advisable to use an analytical scale to weight it, since it is the most sensible instrument. Before the manipulation of the solute, the safety chart needs to be read in order to know which equipment to use and the precautions to take. For example, for the manipulation of the detergent SDS, a face mask is in order. If acids are involved, they need to be placed in a fume hood. Other characteristics of a solute that need to be taken into consideration if they want to be dissolved in a solvent are temperature, the order of addition of the different compounds that are involved, and the pH. This last condition is not only controlled for the solution purposes, the final function of a solution might need to be at a specific pH, like is in the case of buffers. Some solutions need to be sterilized before their use, and the methods implemented for this end depend on the characteristics of the solution. If a growth media is going to have antibiotics in it, the media needs to be sterilized first, and then the antibiotics are added because these ones are denatured at the conditions of the autoclave. If there are volatile elements in the solution, they cannot be sterilized in an autoclave, so the solution needs to be prepared with sterilized water. Lastly, proper storage of the solution is also necessary because even though the preparation process is done correctly, external factors like temperature and light exposure might change the final condition of the solution.
When performing a poorly prepared solution that doesn't correspond to the indicated concentration, it can seriously affect the results of the practice to be performed, since the adequate conditions for performance are not found. In some cases, an erroneous concentration can inhibit the results of the practice, leaving the interpretation of them null. For example, in an agar gel, we couldn't not see the expected DNA bands, or when performing the gel, it wouldn't polymerize, being not useful.
Also, during an electrophoresis, if the loading buffer is incorrectly prepared, the nucleic acids might not be able to set down at the bottom of the well, and in consequence the results will not be visible. For the case of the SDS solution, if it is prepared at a lower concentration, expansion of denaturing proteins will be affected.
In conclusion, in this practice, the importance of the different units of concentration and the calculation required for the preparation of solutions were known. During the preparation, the specific requirements for each solution were observed, and in this way, ensure that the methodology used is appropriate to obtain reliable results and avoid being affected by a poorly prepared solution or with different concentration than required.